What's up, YouTube? I think that we're live already. How's it going? Welcome back to my practice stream. Today we are going to continue practicing fundamental math, or as Serge Ling likes to call it, basic mathematics. So I'm excited about this. We are beginning an introduction to pure mathematics, or in other words, math for math's sake. Math as an art form. Math is interesting on its own, even if we don't apply it to something in the real world. Math is a beautiful art form and game, and it turns out to also be useful, but mathematicians study it just because it's inherently really pretty, and it's really good for your brain, I guess. It's really, really good for your brain. So that's the sense in which I want to be practicing math for myself nowadays. It's just nice. It's a nice thing to learn, and it's better than scrolling TikTok. It's just better than scrolling TikTok. Okay, so yesterday we started this series on basic mathematics, and we started talking about numbers. Just literally from the ground up, from the very beginning, we're going to be talking about mathematics from the ground floor. What's up, Dumb Peppa? How's it going? Welcome, man. Welcome back to the practice stream. So, if anybody's watching this VOD after the fact, this is my practice stream for the day. Later on, near the end of this practice session, I plan on filming a proper lecture on some of the material that we're going to be practicing and covering today. But I want to be, as much as possible, like not always, but most of the time, 90% of the time, I want to be doing all of my daily math practice live. So you get to watch my notebook as I'm practicing and learning math. And so today I'm going to be preparing a lesson plan, or preparing my lecture that I'm going to film at the end of today's practice session. What's up? How's it going, geometry? What's going on, Peppa? Some suggestions to solve trigonometry. This book, dude, seriously, this book is going to help you with trig. It's an excellent pre-calculus book. So yesterday I wrote out the table of contents for chapter 1. I mean, it's something simple, but we could just write out the table of contents for the other chapters as well. Today, I think that we're still only going to be working in section 1 and 2. And yesterday we did work rules for multiplication a little bit, and we worked one exercise there, or a couple of exercises. So, but today I plan on just staying in sections 1 and 2. What happened to camera angle? Oh, are you watching vertically? What's wrong with the camera angle? How's it going? So I don't think anything is different, right? I mean, right now we've got the iPad up. I'm not sure what's different, but okay, so yesterday we started talking about numbers. We started talking about some of the basics, and we started working exercises, including this tougher one. Show that negative a plus b plus c is negative a plus negative b plus negative c. That might seem trivial. That might seem super easy, but we need to be able to prove this very precisely. Like, what is the definition of a negative number, actually? We need the definition of a negative number is a number that is, in some sense, like the opposite number of a number a. So negative a is the number that you can add to a, so that they add to 0, so that they add up to 0. Hey, I study math and physics, then watch your live. It feels good. That's great. That's really great to hear. Yeah, there's a lot of people out there studying. So, if we want to show that the additive inverse of three numbers added together is the sum of the inverses, then we need to show that we can yeah, this line is wrong. Yeah. So we want to show that A plus B plus C. I wrote, this was a typo. The next line was correct, but this line was just straight up wrong. Yeah, plus this all in a bracket equals 0. So I rewrote I wrote that line in the next part. So I can really just delete this line, I see. Thus, the process that we do is we start on the left-hand side. We do a bunch of rewritings until we get to the right-hand side. And here's the approach. Let me just reflow this just a little bit. So, on the left-hand side of this line, I like to use like a little question mark above my equal sign to remind myself this is a claim. Like, I want to show that that line is true. Are they equal to 0? That's the question. We don't want to assume that they are equal to 0. We want to show that they are, that the left-hand side does equal the right-hand side. So you start from the left-hand side, and then we can use the distributive property in a sense, and then we rewrite all of the plus negative A and plus negative B and plus negative C. We write those as A minus B's, or minus A, minus B, minus C. And then we use commutative property and associativity to rearrange and regroup the terms. So this is the same as A minus A plus B minus B plus C minus C. And then each of those three terms are 0. And then, well, 0 plus 0 is 0. Plus 0 is 0. So here's a little proof of this fact. Alternatively, this line, I wrote it just like a little more clearly, although it's still essentially the same proof. What I like here is that now I wrote this line 2 as all additions. In every term, it's still additions, like the addition of negative A, addition of negative B. And we have the fact that the commutative property holds for addition, not subtraction, but for addition. So then, if it's true for two numbers, and we have associativity, we can rewrite this without parentheses and regroup. Like if they're all additions, then you can rearrange the additions as much as you want to. So in this line, I rearranged so that we get the A plus negative A grouped together, the B and negative B grouped together, and the C and negative C grouped together. And then each of those terms are 0. So then they add to 0. So that's the hardest exercise, I believe, in the first exercise set. Sir, is it possible in future you will come up with physics sessions? Dude, if I could do this full time, yeah, I would totally add in physics. But I don't, I mean, probably not, you know? That's not, at the moment, it's not my goal to become a streamer, to become a full-time math streamer. But if I was a full-time math streamer, if we got like a bunch of people signed up, you know, who want to pay me monthly for streaming sessions, and yeah, dude, I would love to study physics live and teach. But that's not going to happen. That's not going to happen. Yeah. Okay, so let's see. All right, I'm going to be reading a bit of this book, and today here's another exercise that we worked yesterday. And I was doing these somewhat intuitively. I hadn't read all of the... Oh no, this one is the hardest exercise from the exercise set. Prove the cancellation law for addition. If A plus B is A plus C, then B is equal to C. So we can, if we have the same number on the left of both sides of the equality, we can cancel those out. The cancellation law. So we worked that one yesterday. It's not too hard. Let's see, what were we going to do next? What I could do is I could, oh, we're not streaming on Twitch yet. Oops. Okay, now we're streaming on Twitch. Okay, so one thing is I could read carefully through the book and take some notes. That's one option. There's no true proofs in section 1, but there are boxed properties and definitions. We have definitions and we have boxed rules or assumptions, properties of the natural numbers. Hey, what's up? Prani Dewan, how are you? So, we can at least do that. Let's begin with writing down the boxed important properties, the integers. So this is a pattern in math books where a important property is like a mathematical result. This is a true fact about numbers, the way that we've defined numbers. Or this might be part of the definition of numbers, but to be really concrete about the rules that we use to define numbers. One of them is that, and often when we have these concrete rules or properties or results, like facts about the numbers, we give them labeled names. Like this is property N1. We have 0 plus A equals A plus 0, and both of those equal A. So this is a boxed important property. We also, for any integer A, adding negative numbers behaves as we are used to. Then we have another property, a plus negative a is defined as 0, and negative a plus a equals 0. Maybe I want my boxes to line up like this. Right? Let's go to IIT. Yeah, man. Let's get into IIT together, everybody. Yeah, dude. Okay, so that's N1 and N2. Remark, we use the name minus a rather than the words negative a. The book uses minus a, but negative a, minus a, most people say negative a nowadays. But the other remark is that you also hear this called the additive inverse. And this is an idea that will pop up again and again in math of an identity element. So this is the identity. The identity property says that if you add an identity to a number, identity, if you use the identity with another number, then they combine to the same number. The identity just keeps the number the same. Identity plus a is a plus identity equals a. I'm using that word instead of 0 right now, just briefly, because this idea pops up again and again and again in math. So that's the additive identity. If I say plus ID is 0, the identity element for addition is 0, the multiplication identity is 1. Why is that true? Well, because 1 times x is x for all numbers x. So this one, the combination let's say, if this was like a programming language, I might say multiplication of 1 and x is equal to x, right? And then in this case is equal to itself. Now, these two are both examples of an identity of, let's say, some mathematical operation of some kind with an identity element and a number or a point or something. And for the first thing to be an identity, that mathematical operation should return, keep the identity, or like keep this other, the second argument fixed. So this might be getting just a little bit abstract potentially, but we see this more and more as we get into more pure math or different number systems. There's not just the whole numbers to work with. Later on, we're going to introduce rational numbers, or we're going to introduce the real numbers or the complex numbers, or we'll go to matrices, or we'll go to other types of mathematical objects, groups. What would be the prerequisite for solving these? This series is supposed to be no prerequisites. This is just introduction to pure mathematics. What's up, Ice Crack? How's it going? So right now this is a practice session, but I will be filming a lecture, a 30-minute lesson video at the end of this stream. So, okay, so I'm reading this section for the first time right now. That's boxes N1 and N2, and then we go to section 2, and I hope that we can get to a proof. Let's see, section 2, 1.2. Now we have rules for addition. Okay. Integers follow very simple rules for addition. These are commutativity. I started talking about this yesterday. Commutativity. It's so important that it gets a name. Commutativity. If A and B are integers, then A plus B also equals B plus A. So this is one of these boxed important facts, and we'll call it commutativity. For example, 3 plus 5 is the same as 5 plus 3. Both of those are 8. With negative numbers, negative 2 plus 5 is 3. Negative 2 plus 5 equals 3. And 5 plus negative 2 also equals 3. Cool. Next, we have associativity. What does associativity mean? If A, B, and C are integers, then I hope you all remember this one. Maybe not, and it's okay if you've forgotten it. If A, B, C are integers, then A plus B, if you add the first two first and then add a third, that's the same as adding the first plus the sum of the next two. In view of this, it is unnecessary to use parentheses in such a simple context, and we write simply, so thus unnecessary to use parentheses in A plus B plus C. The times that you need parentheses are when you add another operation like multiplication. Then you need to group and and make sure that you apply the operations in the correct order. Or if we use, Lang doesn't say this, but I will, or if you use minus as an operation. So we think of subtraction as a mathematical combination of numbers, right? Like a minus b is not the same thing as b minus a, for example. Or a plus b minus c. Well, it is true that this is equal to... Maybe they all are. This is the same as this. But a minus b minus c is not the same as a minus b minus c, right? Is that true? If I want to say that these two are not equal, I just need to have one example. For example, let's prove that. What happens if we use the numbers 1, 2, and 3? This is going to be my first try. Anytime that I see variables a, b, c, what about concrete numbers like 1, 2, 3? Let's see what happens here. This would be 1 minus 2, take away 3 is -1, right? 3 spaces to the left of 2 on the number line. And then this is the same as 1 plus 1, and that is 2, right? But what if I did 1 minus 2 minus 3? 1 minus 2 is -1, minus 3 is -4. So these two are not the same. The second line is not the same as the first yellow line right now. And this is a place where it's one of the reasons why thinking of subtraction is a bit trickier, more difficult to use than if you converted all of the subtractions to additions. Because addition follows simple rules. We don't have to write parentheses for additions. But with subtraction, you do. Does that make sense? So thus, 1 minus 2 minus 3 is kind of ambiguous. We choose this to mean 1 minus 2 minus 3. So if you see this ever in a math book or something, 1 minus 2 minus 3, we choose that to mean this one. 1 minus 2 then minus 3. But we could have chosen 1 minus 2 minus 3. So it's not ambiguous in the rules that we typically always, that almost every single math book ever has always chosen 1 minus 2 minus 3 without parentheses to mean this, but it's still somewhat arbitrary, or it's somewhat it's still a choice. It's still kind of ambiguous, whereas truly addition does not require any kind of decisions, or like, let's all just agree that we add left to right, or that we are subtracting left to right. Addition is commutative and addition is associative, but subtraction is not commutative, and subtraction is not associative. Cool? Okay, so practice sessions. Okay, so associativity. Well, okay, associativity holds with negative numbers if you're adding negative numbers, but associativity does not hold with subtraction. And this is part of the reason why we find using negative numbers, addition of negative numbers, to be so valuable. So the book says the rules of addition mentioned above will not be proved, but we shall prove other rules from them. To begin, if a plus b equals 0, then b is negative a, and a is negative b. So this seems like one of these really simple facts, but it's something that we have to prove. Okay, so this is one approach. You can add negative a to both sides of the equation this way. So then the way he writes is, since negative a plus 0 plus b, which equals b, then b equals negative a. Yeah. As desired, similarly, we find a equals negative b. So let's assume a plus b plus... If a plus b is 0, we can rewrite the entire equation as a plus b plus negative b equals 0 plus negative b. Using associativity on the left, we get a plus b minus b, or even more formally, remember that b minus b means b plus negative b. And adding 0 to anything is itself. So this is associativity and definition of 0. Hey, what's up, Vob Edits? How's it going, man? We're doing just simple intro to pure math, basic mathematics. I'm practicing at the moment. B plus the additive inverse of b are defined to be 0. And then this is also equivalent to a equal negative b. So, seems very simple, very straightforward, or like something that we use all the time. That, like, why can we move b to the other side of that equality and make it a negative? Like, why can we do that? What we're really doing is subtracting b from both sides of the equation, or subtracting a from both sides of the equation. So this is a proof. And then finally we have an example of a real proof in this book so far. And then thus, so when you conclude a proof, you draw a cute little square at the end. So this says, thus it is demonstrated. Another option is, you can, if you prefer, you can write QED. But I like the square. They mean the same thing, but it says it's like a period at the end of your proof, or the end of a chapter, like in a book, and then you begin a new chapter. It's like, we are done. This proof is done. And now in the text, it separates so that the writing right after it, we know, is not part of the proof anymore. That's part of the reason why these cute little squares, or QED, why that's important. Thus, a sum with 3 terms may be written in many ways, like a minus b plus c, we could write as a plus negative b plus c That's the definition of what A minus B means. And then we can write this as this by associativity. We could also write this as this by commutativity. We could also write this as A plus C minus B by associativity again. Right? If we're getting confused here, let's go back to numbers. 1 minus 2 plus 3. He doesn't write these examples, but I like to fill in the details or like see an example without A, B's, and C's. Let's just see, what if we rewrote all the A's as 1s, all the B's as 2s, and let's see what happens here. That we claim that this is equal to 1 plus negative 2 plus 3. Is that also equal to is that also equal to 1 plus 3 minus 2? Is that also equal to 1 plus 3 minus 2? So we're just getting one example without A's, B's, and C's. I believe that this is true all the time for every numbers A, B, and C because we've already shown that it's true in general. Cool. You're listening to an intro to pure mathematics through your guitar amp. That's cool, Ta. That's really cool, dude. What are you practicing? So we've been working with truths and we've been proving facts about any numbers, A, B, and C. And it's so valuable to be working with arbitrary numbers. But every now and then you want to go into a concrete example. It's very valuable to have examples. So if we worked this, 1 minus 2 plus 3, what is 1 minus 2? I know that sounds really simple, but if we are thinking of subtraction, I think of moving left on a number line. 1 take away 2 will land at negative 1. And then if we add 3 to that, we jump forward 1, 2, 3 spaces. And we get to the number 2 on the number line. Right? So this number, 1, 2, yeah, I think I did. 1 minus 2 is negative 1 plus 3 is 2. Yep. So this number ends up, like this approach ends up being positive 2. Over here, 1 plus negative 2 if you add negative 2, that is literally just the same. That is what it means to subtract 2. We are adding there's another way we could write this. We could write this also as -2 plus 1, and he missed this fact, but it's because it doesn't fit neatly in one single list of equalities. But notice that we also get -2 plus 1 plus 3. And yeah, we can write even more alternatives. This also is the same as -2 plus 1 plus 3. That also is equal to -2 plus 3 plus 1. So there are many ways that we can rewrite a addition with 3 terms. But again, addition of -2 and 1 is the same as 1 minus 2. And then if we add 3, 1, 2, 3, we jump forward 3 spaces. So that's the same diagram to get to the fact that this is +2. But now here, this is a little bit different. On this one, we would be rewriting this as 1 plus -2 plus 3. -2 plus 3 is +1. 1 plus 1 is 2. So it's like it's kind of like this one requires 2 different rulers that you're working with, or yardsticks or something, number lines. Like first we find what is -2 plus 3. -2 plus 3 is 1. And then you figure out, like, you take a break, you do something else, and then you come back, and now the new question is, what is 1 plus 1? 0, 1. 1 plus 1 is 2. And so eventually we also get that this is 2. We got that this one was 2. We got that this one is 2. Similarly, this one requires 2 separate additions. Like first, day 1, you're going to do this math problem. 3 minus 2. So here is 3, and then if you take away 2, you start from 3, and then you subtract 2, and you get to 1, right? So this problem is now simplified as 1 plus 1, and then again, 1 plus 1 using this ruler, or this addition path, ends up being 2 as well. Like, none of this is surprising, but I'm showing how the facts that we're using associativity can be thought of as the order in which you're doing these additions, and how these are different ways to write a simple addition with 3 terms, like Lang pointed out. This last one, if we start at 1, and then we add 3 to it, then now we're at the number 4, and then if you subtract 2, then we're at the number 2, right? And those are different paths through like how to combine those numbers and all of them add up to 2, as you'd expect. I wonder if that makes sense. I don't know. I think that that's a valuable example. Okay. As a special case, let's remember that N3 meant N3, the boxed math fact N3 was if A plus B is equal to 0, then then B is equal to negative A, and A equals negative B. As a special case of that fact, we have A is the negative of negative A. So if we've shown and we've proved this result, which we did earlier, then we get this as a special example. So right now, this is in the form of x equal negative b, or negative y. Just making up other letters just to remind that that's the shape of how that's written, in a sense. We prove this, I think, through the definition that A plus negative A equals 0, then A equals negative A. The first one is like the definition of negative A, and then the second one applies that last result, N3. Is this suitable for me? I am 16. Absolutely, dude. I think that this is suitable for anybody. Yes. Like, somebody who's motivated and wants to learn this kind of math, which is argument-based, and it's pure math. It's more based in logic and reason, like the reason why things are true, and conceptual math. Somebody could start learning that from day one, I think. Yeah, so what's up, Tiger Bro? But also at the same time, it's a type of math that many people have never seen before, like that most people don't see in high school, like at least in the US, which is, I think, a shame. So in some sense, this math is beautiful math available to everybody, to most people. Yeah. Yeah, so as a special case of N3, we get this. Lang says this is true because A plus negative A equals 0. Yeah, exactly like how I wrote it. He says, yeah, this is true because A plus negative A equals 0. And then we can apply our previous tool that we built, N3, where B is, we replace B in our tool N3. Where the heck is N3 again? We can apply N3 where B is negative A. Right? Is it rigorous? That's the idea. Yes, you've heard the word rigorous math. In the US, we don't really teach rigorous math in the standard curriculum. Like a good middle school or high school teacher will teach it, but it's not required on our state exams, on like in our standardized testing in the US, we don't require rigorous proof-oriented math. What's up, Arad? We're proving little simple facts about numbers, you know? It's always fun to work with the fundamentals, I feel. Remark that this formula is true whether A is positive, negative, or 0. If A is positive, then negative A is negative, and blah, 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 blah. In the geometric representation of numbers on the line, A and negative A occur symmetrically on the line on opposite sides of 0. Of course, we can pile up minus signs and get other relationships like negative 3 is the same as negative, negative, negative 3. Yeah, things like that. For the general formula with appropriate notation, check out an exercise 5 and 6 of section 4. From our rules of operation, we can now prove for any integers A and B, we have this. Okay, so he says we can now prove for any integers A and B, we have negative A plus B is equal to negative A minus B. This is a beautiful proof. Another tool in our toolbox of numbers. I suppose that's why he's using N. These are all facts about the numbers. Hey, what's up, Holmes? How's it going, dude? Okay. Okay, so now we have a new tool in our tool set that we can use if we can prove it. I'm going to try before I read Lang's proof. And this is because this is a practice session right now. So I want to be showcasing my method of reading mathematics and how you can be actively reading before you just jump right to the solution, before you immediately start reading the solution. Try to prove it for yourself. Why is it specified as integers? Is it invalid for other numbers? Nope, you're right. It is true for other numbers. But so far in this book, we haven't invented other numbers yet. We only have the integers, which are the numbers that we can use to count how many acorns I have, how many M&Ms you have, how many times I've said the word 6, 7, in this stream, right? Like how many, like counting, like we only right now have the math. We've only invented so far the math about counting. We don't even know yet that there are other numbers. And later on, when we invent other types of numbers, we'll see that this is also true for the rationals or other weirder types of numbers. So far we only have integers. Proof. I'm going to try this on my own. So let's see. We want to show that a plus b plus because this is the definition of negative a plus b. The definition of negative a quantity a plus b is the number that you can add to another number so that they equals 0. We begin with the left-hand side. A plus b plus negative a minus b. By definition of negative a and negative b, I was saying negative b, but this is negative a minus b. It's written as a subtraction, but the subtraction means adding negative b, right? Now this is written as all additions. So we can apply the property of omitting parentheses for a group of additions. We had that, this is repeated associativity. We could call this repeated associativity in addition. Parentheses are somewhat unnecessary if every term is addition. So I can lose the outermost parentheses, and now we can use commutativity to regroup. And now a plus negative a, by definition, is 0. B plus negative b is 0. And now we have 0 plus 0 is 0. This was working. This is a proof relying on what are the math facts that we really used here? Well, certainly the definition of negative of a negative number. We relied on mostly associativity. Of addition. We relied on commutativity of addition. And that's it. So Lang said that we could now prove this fact. So I think that there might be another proof. Cleaner or simpler, more elegant, relying on N1, N2, and the new tools, the new facts about numbers, N1, N2, N3, N4, and N5. Let me remind myself. Okay. Wait. No. So commutativity and associativity are not given names. What is N1 again? N1 let's remind ourselves is this fact. 0 plus A is also A plus 0 is A. And 2 is A plus negative A equals 0 and negative A plus A equals 0. And 3 was if A plus B equals 0, then B equals negative A, and A is negative B. And 4 is A equals negative A. And N5 is negative A plus B equals negative A minus B. Oh, wait, no. Right now we are trying to prove this is our goal at the moment. And we may be able to use these other facts to get it. So let's see. Can we do a second proof? Proof 2. So we know that this is true by definition. Okay, I'm just going to read his proof. I'm not seeing it immediately. Let's just read. Maybe he just showed exactly the argument that I had over here. I think it's possible that he just did the same exact argument, and I may have been using one of those facts without even realizing it. But, like, the fact that he says, like, we can now show N5, I'm guessing that we can use N4 to show N5. So A plus B on the left-hand side then would be negative, negative A plus B. So if I replace A's with A plus B, we have this. But we don't know what I still feel like we may need N3 and N4 or something. If we use N3, now, this is true by definition of what negative quantity A plus B is. Then N3 would prove that negative A plus B equals minus A plus B. I mean, that doesn't really get us anywhere. Oh, wait, oh. Wait. If we use the second part of N3, we get A plus B equals negative of negative A plus B. And then using N4, I mean, we're still getting... Yeah, if we use N3 and N4, then we are back to this. And that doesn't really get us anywhere. Let's see. Yeah, real numbers are very complicated. It's actually, very non-trivial. Great questions, man. Yeah, it's hard, actually, to define concretely, like, precisely what a real number is. It requires kind of an upper division math class, which is fascinating, right? Hey, you're preparing for JE. Good luck, dude. I hear it's very hard. Yeah, Dedekind cuts. Okay, so people in chat are asking about the real numbers. Without vague definitions, like a rigorous definition, without just saying it's every number between two numbers without describing decimal points. Like, what is a decimal point? You have two real options. Something called Dedekind cuts. And you have another option called using Cauchy sequences. This is the approach that my course focused on. And these are sequences of numbers that converge to a limit point. This requires things like, if you haven't yet seen this, this requires the epsilon delta. I mean, I think both of them do, but both of them require the epsilon delta definition of the limit. So there's some starting points, and we can be talking about this stuff in more detail next week when I'm doing calculus streams. Yeah, I'm a Cauchy sequence enjoyer. Me too. Nested interval method is good too. I thought nested interval was Dedekind cuts. To be honest with you, I've never really learned Dedekind cuts. I know that I feel somebody should, don't clip that. Don't clip that. Somebody will get very mad at me. But yeah, I've never really learned Dedekind cuts properly. I think I've seen the basic idea, but I would not be able to relay it at all. So I'm a little stuck here as to why Lang is saying that N4 implies N5. I feel a little silly about it, but I suppose if I start with Let's just read it. Okay, let's just read it. Cantor diagonalization proof. Whoa. These math words sound like delicious foods. Yeah, nice. I mean, yeah, pure math is very delicious. Okay, so let's just read Lang's proof here. Proof. Remember that if x and y are integers, then x equals negative y and y equals negative x means that x plus y equals 0. So I was just saying definition of that this is the definition of negative numbers. It's the number that you can add to another number to equal so that they add to 0. Hey, dude, Lockheed, I wanted to ask, if you don't mind, I love your comment in the Discord. By the way, shout outs to the Discord if anybody wants to hang out with us after the show. It's a nice little group. I loved your comment about like the hatred of high school geometry is palpable, or that you feel me on the hatred of high school math. If you don't mind commenting that publicly, I think that's a funny comment. I don't hate high school math, but I agree with your sentiment. Like, you also feel the same way. I'm glad. I'm glad that somebody else says it, because it's like high school geometry, like you're learning geometry and you're learning proofs at the same time, and neither of them seem clear like why it's useful. It's like as if proofs are only useful for this type of math, which is completely different than all the rest of math that you learn everywhere else. It's like you get like a little introduction to showing that triangles are congruent or that angles are congruent, like with parallel and intersecting traversing lines and things like that. And then you learn that and then you forget it. Like you don't really use it in the rest of your pre-calculus classes. Other than like area and volume formulas, which I don't even know if you really prove in high school geometry anyways. But like that method of proof, it feels as if it's like only useful for this antiquated old school math that we no longer really use or something. But proof is math. Like math is proofs. Math is conceptual arguments why some new math claim is true, right? I was amazed when I learned some infinities are bigger than others. It's an informal way to say it, but well enough. Yeah, absolutely. You haven't opened Discord in a while. No worries, Levi. Yeah, no worries about that. But yeah, also Levi and everybody in the chat, I should really link this in a pinned comment. Dude, new video. I hope you check it out. It'd help me a bunch if you watch it in full. Watch the full thing and leave a comment. I'm announcing my new series in pure mathematics, Intro to Pure Mathematics. Math Can Be a Hobby. New video. I don't post videos very often, but this one, I would love if y'all would give that a watch, maybe after this stream. Yeah. Thanks. So, new video, Math Can Be a Hobby, Intro to Proof Math. New video. Announcing Intro to Pure Math. So, go check that out. Okay, so we're getting a little distracted, but Lang reminds us now, which is good math writing, I think, to go back to the definitions. Don't just immediately jump into it. I don't like Yeah, you don't like geometric proofs. They can be very misleading. Yeah, like, I'm glad I'm not the only one. Because it's super true that, like, proofs is real math. And geometry is math, but it's only one type of math. But we learn it like as if proofs are only useful for geometry. But proofs is in some real sense like real math. Like that is what actual mathematics is. And it's a shame that we don't see proofs in pre-calculus stuff, in number theory, in basic numbers. Like you do, but it's not presented that way, and definitely not as concrete and rigorous as something like this. Okay, so he says, thus, to prove our assertion, we must show that A plus B plus negative A minus B equals 0. Cool. So this is exactly how I started my proof. So I'm on the same exact. I will catch you all later. Lovely stream. Nice to meet you, Tiger Bro. Nice to meet you. Check out that that new video when you can. And it's good to have you. Good to have you here. I'm very happy to be introducing people to proof-oriented, pure mathematics. Cool. So we must show that this line is true. This is our goal right now. But this comes out immediately. Yeah, okay. We did the same thing. But he uses this language that I don't like, that's like a little offensive or something. Like, but this comes out immediately. Like, oh, this is obvious. Like, Lang is a little infamous for this. Like, not just in this book, but in graduate level books. He makes you feel kind of dumb sometimes. Like, this is bad math writing. I would say, like, there's no reason to say it, but this comes out immediately. Just say, we see this. This is true because ... Move that out of the way. We see this by this is equal to A plus B minus A minus B by associativity he writes it out, associativity. This equals, what's his presentation here? A minus A plus B minus B by commutativity I'm running out of space there, but and this is equal to 0 plus 0 by definition of minus A and minus B, and 0 plus 0 is 0. This proves our formula. Okay, so we did the exact same thing. He doesn't draw the squares, but I love the squares. Hey, what's up? Learning how to compute integrals is different than learning what is integrals actually. Yeah, I mean, that's true. I like to divide math in two categories, structural and computational. Yep. Hey, what's up? Harshagar Walarts. How are you? Nice to meet you, man. Do you like math? Are you a math person? There's some interesting commentary saying that there's a rule that we don't even think about using because it just seems so natural and obvious or something that we don't even realize that we're always using this fact that if A and B are positive, then A plus B is positive. Like you need to... If you're going to use that fact somewhere, you need to at least prove it to yourself that that's true somewhere along the way. We assume this rule concerning positivity. We shall see later that it also applies to positive real numbers. From it, we can prove if a and b are negative integers, then a plus b is negative. That requires a proof. Neat. We're almost done with every proof, and I'll do the last example in this section. And now, so he doesn't give this a boxed name, but he says, just from it we can prove something like, I don't know, he says, we assume if A and B are positive integers, then A plus B is a positive integer. From it, we can prove if A and B are negative, oops, so this is a new math fact. How do we prove this? If A and B are negative integers, then A plus B is negative. So this means that A is negative of negative A, and B is negative B, where negative A and negative B are positive. Maybe. Then A plus B is negative A plus negative B. And didn't we just show that oh wait, no. A is negative A and negative B. And our previous result was saying that we can factor? Question mark? Now this is two positive numbers added together. So now this is the negative of a positive number, which is negative. Okay. I think that that's the proof idea. But I got a little hand wavy, and I want to be very formal and follow the proofs. we can write, yeah. I was thinking that you could do this, introduce a new letter. I was considering this. We can write A is negative n and B is negative m, where n and m are positive. So, yeah, he wrote that, whereas I was saying specifically n and m are negative a and negative b. But we wrote something extremely similar. Therefore, a plus b is equal to negative n minus m, which is equal to negative n plus m. And this equality is true by N5, by this tool that we built earlier. We built this tool that the negative of a sum is the sum of negatives. So the sum of negatives is the negative of a sum. And which shows that a plus b is negative because n plus m is positive. So we did the exact same basic mathematical argument. He just wrote it like a little more clearly, and that's what I felt. I was like, this wasn't as clear as I'd like. Yo, Psycho Kowalski on Twitch. Math sucks. And Kruk, how's it going, dude? I just saw the raid. Thank you for the raid, bro. How was your stream? How's it going, dude? Are you... Dude, nice to see you. What were you practicing? You met me last night from guitar, right? So you might be surprised to see me practicing math at the moment. What do you stream, dude? What do you stream? I don't even see. What do you stream? Oh, you play the violin, piano, and video games. Let's go, dude. That's awesome. Well, hey, if somebody raids me, if you want, I'll play a guitar song. Can I play you a guitar piece? Yeah, Harsh says, I want to know how math actually works. That is the whole idea here. This is the whole idea of a intro to proof based or pure mathematics. We only care about why things are true. Sort of. But we 99% of the time we're focused on why are things true rather than examples where it is true. We leave that to the engineers. we let the engineers and the business people use math, and we care about proving math. We're building math for other people to use, in a sense. And in order to build new math, we need to understand how math is built to begin with. Does that make sense? All right, dude, Kruk, can I play a guitar piece? I want to encourage raids. Good to see you, man. You got an exam tomorrow. That's awesome. Yeah, let's do it. Thank you. Thank you for indulging me. Cool. So, I mean, this is just where, like, even for people who think that math sucks, I don't know. I bet you don't have an opinion on pure math. Like, I bet you haven't seen pure math. So, it's why I insist to adults, consider learning pure math as a hobby, because it's actually really beautiful, and it's very different than the math that you learned and that you have bad memories of. I literally didn't get interested in math until I went to college. I was okay at math. I was like decently good at math. You know, I passed the AP Calc exam. I wasn't bad at math. But I wasn't interested in it until I met mathematicians. Like, it's very different. Until I started seeing proofs. Psycho Kowalski. I'm only interested in math that blows up my enemies. Reasonable. Okay, what do I want to play for a raid? Cold. Let's do Villalobos. I showed you Villalobos Prelude 4 last night. I wanna show Villalobos Prelude 1. I like this one a lot too. This was written in the 1940s by Brazilian composer Heitor Villa-Lobos. He was a big deal, not just in classical guitar, but also a lot of his cello compositions and concertos and other things, symphonies that he wrote. But yeah, hope you enjoyed this. That was okay. For a completely cold take, I'm happy for that. Like, I literally haven't touched the guitar yet at all today. So definitely not as good as if I actually warmed up or played it before today. But hey, for a completely cold take, I think that was good. Thanks, Croc. I appreciate it, bro. Thank you again for the raid. I will try to catch your streams. When do you stream? What days? What times? Yeah, I'll try to catch you sometime. HVL preludes always have a sense of conflict in them, don't they? Yeah, HVL preludes are just so freaking gorgeous. They have this edge to them. They have this 20th century, like, kind of freaking, like a little edge, like a little bit of conflict. I think you're right. Like, that's a good word for it. And hey, dude, look at this. I love it. Thank you, bro. Feedback is always a gift. Sundar says, what is that weird sound in between? Is it due to the friction when you move your finger across the thinner part of guitar by your left hand? Is it a part of music or error? Try not sliding it if error. Yeah, so good. Yeah, no, you're right. Sometimes there's a difference between string noise and squeaks. String noise is part of the guitar, and it's like... Do you hear that? That... Like... There's like kind of a sliding sound. That is intentional, and that is correct, but like... Other times, other times it's a squeak and it really just is wrong. Like a squeak is... That sound you don't want. And yeah, it's a technical error. Sometimes, like this one I want. Let's see. I'm not warmed up at all right now, but there are times, yeah, you definitely want to lift the finger before you do shifts. Sometimes. Most of the time you want to avoid that string noise. I'm mixing up 2 different HVL preludes right now. And yeah, dude, thank you for the feedback. Also, I have no experience in guitar, but it seems you're moving by looking. Yeah, it's not a bad thing to look. Like, you should look at your destinations, but you should also be practicing it without looking. Like, there's nothing wrong with looking. It can really help, and it's not considered bad technique in classical guitar. But you kind of want to be able to play it both ways, and I do practice it both ways. Hey JC, came for my coaching. We'll be back to studying soon in 30 minutes. Awesome, dude. All right, let's get back to it. Let's finish up this. Let's finish up the stream. So we did all of the proofs and we learned all the theory. We saw all the proofs in section 2. So let's see. Example, if we have the relationship between 3 numbers, we can get examples and solve equations. So this is just theory. This is now just an application of the theory, of the general theory that we've built. So example, if A plus B equals C, then we can derive other relationships between them. For instance, we can add negative b to both sides. Can add negative b to both sides. A plus b minus b is the same as c minus b. Whence a plus 0 equals c minus b, and so a is equal to c minus b. Right? This is like one of these rules or one of those facts about algebra of how to solve equations that we use all the time. So if a plus b equals c, then a equals c minus b. Like, we can rewrite and we can solve equations by adding a number to both sides of the equation. Similarly, we also get b is c minus a. For instance, for example, if x plus 3 equals 5, then x equals 5 minus 3, which is 2. If 4 minus a is 3, adding a to both sides yields 4 minus a plus a. 4 is 3 plus a. Subtracting 3 from both sides, we have 1 is equal to a. Another example also, if negative 2 minus y equals positive 5, then negative 7 equals y. So how do we get that? You could add y to both sides and then subtract 5 from both sides of the equation. Or you could write it in the other direction. So these are just examples. These are just like little examples of the theory that we built. These boxed yellow facts. This is, in some very real sense, this is the real math. Like, this is the general facts about numbers that we want to understand. And we want to spend most of our time understanding general facts about math. And then, after we understand those general facts and we have proofs that those facts always work, once you have proofs and we're confident that those tools, that those things are true, once we understand why addition works this way, then, like, once you're confident about that, then any of these types of problems are just an application of something that we understand in more generality. Like, we understand how to solve algebraic equations in general. So these are just little examples. These are just examples. And there's nothing too magical about them. Like, filling in the details on something, on this hardest one, then we can rewrite this by adding y to both sides of the equation. This one is the same. This is using the math tool, the math fact. Well, maybe it might have been in the previous section, but I would write this out. If a equals b, then a plus c also equals b plus c. This was called the cancellation law. Oh, and it's an exercise, isn't it? It's an exercise. But it makes sense that we're going in the other direction, I think, needs proof. But if a is equal to b, you can add c to both sides. And that's all we did. We added y on the left and we added y on the right. Then this is, by associativity, I'm just really explicitly showing the regrouping here. Negative 2 plus 0. Negative 2 is 5 plus y. And now I can subtract 5 from both sides of this equation. On the left, I can subtract those two. On the right, if I'm going to be really annoying, I'll write this line too. Here I used commutativity of addition. I regrouped. And now negative 7 equals 0 plus y. And then negative 7 equals y. So we don't normally write every single individual step along the way like this, because we get used to much more quickly going through all of those in one step. Like add y to both sides, subtract 5 from both sides, bada bing, bada boom. We go from that one to this one. Or you can write an equality in either direction. Yes, I do want to get Twitch chat on screen. I don't know how yet. I'm trying to figure it out for sure. Good luck with your beard. Yeah, I don't have any tips on that. It took me a long time to be able to grow even this like disgusting scraggly beard that I have. So these are all of the individual details, and a computer will go through every single individual detail. But as humans, we can kind of jump ahead and we can see like, oh, when I add y to both sides, then the y's cancel. The right-hand side has 5 plus y. Then when I subtract 5 from both sides, negative 2 minus 5 is negative 7. 5 minus 5 is 0. Then we have 0 plus y. Then we have negative 7 is y. I could rewrite that in the other direction, and y is negative 7. You can kind of, like, after doing this a few times and doing it in the tedious level of detail, then doing this in one line, in one step, becomes very easy. And it's clear why it's true. And all of this is clear why it's true because we've shown that it will always be true with these math facts that we've invented and we've constructed one piece at a time. Yeah. So there's our introduction to pure mathematics today. I don't think I'm going to run my lecture today. I know I said I would at the beginning of the stream, but this is already gone for 2 hours, so yeah, no worries, all good. The human brain is a biological simp from Lean. Yeah, even if you're writing a computer program to do it, it's a little tedious, and you can just tell the program like, hey, just keep trying, keep applying these basic rules, and all of this we would call simplifying. To simplify an equation is just again and again using associativity, commutativity, definition of zero, definition of negative numbers, and you just kind of throw that into the blender, and eventually it's, you eventually get any of these kinds of rewrites. We just call this simplifying this equation. Just throw these basic facts and some of the other ones that we've proven so far, like N3, N4, N5, and using those math tools, those math facts that we've invented and built one Lego block at a time, this will get rewritten as y equals negative 7. We can also calculate similarly. We keep guessing what the whole sentence could be by our previous training data, just by initial words, very similar to how computers do. Yeah, I mean, that's that is more like the pattern matching approach of math. So I disagree with you. Like, this form of math is constructive, and it's step one leads to step two, leads to step three, and everything is very carefully built one bit at a time. Another approach is like to see a lot of examples like this, just see a bunch of examples and get used to seeing some general, kind of mnemonics, like, oh, you move y to the other side and you change the sign. And then, when you move something to the other side, then you change the sign of the thing, and then you have your simplified version. Or combine like terms. Like, yes, we are combining like terms, but what we're really depending on are these math facts. And it's so important because we think like, oh, this is trivial, this is no big deal. But it turns out that there's other places in math where these kinds of facts don't work. And you can't use your intuition. Like, you're used to the idea that every number has an inverse or something, that every number has a negative number. That's not always true. If we only have the positive numbers and we only work with the positive numbers, we can add any two numbers, but we can't, there's no number, there's no solution to this equation if the only numbers you're allowed to work with are positive numbers. And that may not seem like a big deal, but it is, because sometimes we do want to work only with positive numbers. I've never actually written this on the screen today, but Z is all of the positive and negative integers. N is the set, I'm going to include 0 and all positive whole numbers. Some books will include 0, other ones won't. Don't worry too much about it. But so in the integers, there is a solution. But in the natural numbers, there's not a solution. What's another example that people may have seen before of another type of equation? X squared plus 1 does never equal 0, with the decimal numbers, with the real numbers. I should just say real numbers. But x squared plus 1 can equal 0. This does have a solution in the complex numbers. These are different number systems with different mathematical results, different math theory, like all these math facts that we've been building. Some of these are true in some number systems, and some of them are not true in other number systems. Another example, A times B equals B times A in the integers. It's true in the rational numbers, in the real numbers. But A times B does not equal B capital A times capital B does not equal capital B times capital A in the set of matrices. Maybe they're matrices with real numbers in them. But for simplification, I'm just going to call this the set of matrices, which are blocks of numbers. And math is about discovering other, we start with the simplest possible numbers. These are the counting numbers. to count how many times I've said 6, 7 today or in my entire life, right? At one point there was 0. Right now I just said it once today and probably 100 times in my life. Then we extend. I mean, there's no need for negative numbers if I'm counting how many times I say the word 6, 7. But if I want to talk about time, like if I wanted to talk about how many hours ago yesterday was, we need -24. Like, there's time before now and then time in the future. Maybe in the past, we use negative numbers. Real numbers, you need to invent that for certain types of questions. Complex numbers, you need to invent those for different types of questions. Matrices is another field of math, but what facts about about these simpler forms of math are true in more complex forms of math? Which of these, simpler truths are still true? This is broadly kind of the idea of proof-based constructive mathematics. Like, we're constructing all of the truths that we're going to use in later, just building Lego block by Lego block. And I know I'm going to make some people mad by saying constructive math, because so far we've only done constructive math. But okay, let's see. Let me read chat. We can also calculate similarly. We keep guessing what the whole sentence could be by our previous training data. The fact that statements independent of axiom systems exist is kind of spoopy or spooky. Yeah, that's another amazing fact. Like, our goal is to prove all true statements about math, but it's a beautiful and crazy kind of quantum mechanics revolution in math in the 20th century. About 100 years ago, we discovered that there are truths in math. There are true statements that we will never be able to prove in this method. Like Bob the Builder, we can build it. We were so confident. Hilbert was like Bob the Builder, saying like, we can build it. No matter what, we can build it. We will start from the axioms, and eventually we will understand questions like, is there an infinity? Fact is, there are different sizes of infinity, and we'll talk about that in the future. But we don't know, still to this day, whether there is an infinity that's bigger than the natural numbers and smaller than the real numbers. This is it has to either be true or false in some sense. But Hilbert, says, yes, we can build it. We'll find this way. And somebody named Kurt Gödel said, nope. Give up, bro. Which is amazing. Like, this is actually amazing. There are math facts that we can't prove. You have to make this a little bit more precise, and you have to, fill in some details of what we mean here very precisely, but this is the general concept here, and it is true. Like, there are math facts that we with the math that we have right now, we will never know in the method, in the way that we did math so far today, we will never know if there's, you know, an infinity between these two different types of infinities. That's amazing. There's so many ideas in that most people have never seen. Most people have never heard of different sizes of infinity. Yeah. So it's amazing, like, to me. And this was shocking to people 100 years ago. I really think that this is quite similar to quantum mechanics. Physicists still say that nobody really understands quantum mechanics. It's so weird. This is like that quantum mechanics revolution in math about 100 years ago. Cool. Ooh, this might be a good place to talk about some category theory about the universal properties. I don't understand that well enough to be able to explain it right now. Can't prove and can't disprove. Yes, true. Anything that, if there's a math fact P that we can't prove, then we also can't prove that the opposite is true. You're right, yes. These two are equivalent. Like, we'll never know yes or no, true or false, that there's an infinity in between the two. Like, we don't know, and in some sense we've decided that that's a pointless question to ask, which is cool. What? Are you serious? Wait, Gödel found an inconsistency in the US Constitution. I think Einstein and others had to talk him out of that insanity. Oh wow, that sounds really interesting. I haven't heard about that one. I know that Gödel had some like really interesting philosophical writing that we don't talk about as much. I think he wrote about religion and some other things. But yeah, Gödel is fascinating. Very interesting person. Okay. I'd have to learn more. Yeah. Yes, I think I remember what you're referring to here, that something is independent of ZFC requires both showing that it can't be proved and that it is meaningful or something. What level math is this? It is basic mathematics. It's returning back to the basics, but in like hard mode. Like, we're going to go back to the numbers, dude. We're going to go back to 1 + 2 = 3. But we're going to go to hard mode of the simplest math ever. And we're going to learn proofs. Anybody could learn this. Like, a really, really smart kindergartner could learn this if they wanted to. Like, a really smart... Like, somebody could start learning math this way. Probably not a good idea, but... proofs are returning back to the basics and understanding the concepts of why these things are true, rather than just focusing on examples and specific cases. Oof. Yeah, I know that the complex numbers are the algebraic closure of the reals. Neat. Ooh, okay, cool. integers are the Grothendieck group of naturals. I don't know about that. Dude, I want to learn this stuff. I know who Grothendieck is, and I know broadly, that he worked in algebraic geometry and did a lot of category theory work of this kind of fundamentals that you're talking about. Like in math, the US high school system lies to you because it says that numbers are easier than fractions. And that once you're done with fractions, then those are easier and you're done with them until you get to the real numbers, the irrational numbers. Right? And irrationals are even easier than polynomials. Or something. This is a lie. Like, there are mathematicians, the most pure and beautiful field of math is called number theory. And a lot of the best mathematicians in the world today, some of the smartest people in the entire world right now, only care about questions about numbers. And this is where some of the hardest problems are. I don't know. Mathematicians are going to get mad at me for saying that. But I mean, some of these questions are so simple that we don't know how we would even tackle proving why some math pattern works or something. Your streams always make me feel so dumb. Well, that's the opposite of the goal, for sure. Yeah. I mean, I do want to show people that even though we're just talking about literally, dude, we are just talking about 1 + 2 - 3. Like, this is the math that we're focused on today. We are focused on this math, and we all know the answer to this, but there's a level of depth that most people have never seen. Like, this path is a lie. I think that the right way to learn math, that you do when you go to college, you learn the easy stuff, then you learn some harder stuff, then you come back to the easier stuff, and then you keep coming back, and you keep, like, finding new math, and you keep, like, discovering new tools, new math facts, and then come back to the simple stuff. And it's more of a spiral where this direction you get breadth or new concepts, and every time that you keep coming back, we're getting more depth. So we're studying now facts like 1 + 2 - 3 in more depth, with more maturity, with a different amount of life experience, and things like that. Right now we teach this in elementary school or kindergarten. I don't know. When do you go to kindergarten? Like when you're like around 5 years old or something? I think people learn that when they're about 5 years old. And then you don't see it again until you're in college. And you're like, about 20 years old or something. That's ridiculous. Like, I think that we could be learning this level of math where we're talking about questions like A + B - C, and we're proving all of these facts for any numbers, I don't know, when you're 10, 15, some level in high school or middle school, to talk about some of this math about numbers, prime numbers, rational numbers, fractions. There's a lot of depth that you learn about all that stuff, but usually you don't see it until you go to college, or if you learn it on your own as a hobby as an adult. Hardest part of math is pretty subjective. Yeah, I know, that was extremely hot take, or like, that's not true at all, that number theory is the hardest, but that I meant to say that some of the hardest problems like the Collatz conjecture, like what is the really deep connection between these two? The Collatz conjecture, which we'll do a proper stream on, like a proper film lecture on, there's a really deep mystery that connects these two. And 100 years ago, we found this pattern that we'll talk about later. And somebody named Erdős, who is one of the most prolific mathematicians of all time, said, math is not ready. Like, we have no clue. Like, we need brand new tools. We need brand new math facts and theorems and we need a much bigger toolkit. We cannot build this yet, even though this is so simple. So that's what I meant by, like, some of the hardest questions that feel like they're, like, out of reach because we have no clue how we'll prove them. Some of those are in number theory. I mean, there's Fermat's last theorem. This was proved in 1994, I believe. And it's such a simple fact about numbers. Yeah, someday we'll prove 1 + 1 = 2, and it'll take a month or a week at least. Well, no, it depends on where you start. If you start from the Peano axioms, I've done that already. I've already proved 1 + 1 = 2 in using Lean. We'll do 1 + 1 = 2 from the Peano axioms using a computer program, but to prove it to the level that what's his name proved it in Principia Mathematica, Bertrand Russell and Alfred Whitehead, is that his name? Yeah. Take one apple, take another apple, how many apples you have? 2. What else proof do you need? See? Oh, my sweet summer child, there's more to it than that. In my experience, it would be algebraic geometry. Yeah. I mean, specifically algebraic geometry came to mind when I was writing that. I was like, I think some category theorists and algebraic geometers would disagree. But maybe that's just because you and I are consuming the same pop science math. Like, we're both reading the same Reddit threads or something. Like, neither of us are mathematicians. We're both hobbyists. Like, I mean, I'm a mathematician in the sense that I'm getting paid to teach, to tutor, but I'm not a research mathematician. I'm not qualified to say what are truly the hardest problems. But bro's smile is precious. You're gonna make me blush, dude. Thank you. Veritasium. Oh yeah. You saw Veritasium's video. Awesome, dude. I look forward to posting my video on it. I think maybe at the end of the week or next week. I think next week I'll have a nice video on it. Yeah, I don't understand how you go lower than the Peano axioms too. Like, yeah, Principia Mathematica, I've always been like, I don't even want to understand why. Like, okay, dude, seriously? 100 years ago, somebody wrote a 300-page book with the goal of proving that 1 plus 1 is 2. And it was about 300 pages of the type of math that we were just doing one step at a time. And it, you know, this is morally true. I have no idea if it was 300. I know it was hundreds of pages long. And this was one of the main results. Or at least it took hundreds of pages to prove this. And that's kind of crazy talk. Like, you got to stop and, you know, at some point, we got to just believe it. We need to start believing this. We don't need hundreds of pages to prove this one. Even the Peano axiom approach, yeah, Peano axioms don't take very long to get there. In Peano axioms, there's only the number 0. The only number that we have is 0, and then we have the successor function, which is basically plus 1. Plus 1, every number is just adding 1 many times to 0. So we only kind of have 2 numbers, 0 and 1. Well, yeah, we have 0 and plus 1. You can always add 1 to a number. And so 1 plus 1 equals 0, or 1 plus 1 equals 2. Doesn't take very long in Peano axioms. We're saying that the successor of 0 plus the successor of 0 equals the successor of the successor of 0. Or something like this. What does plus successor mean? It means that many successors. I'm talking out of my butt right now, but it's in Peano arithmetic, we build all of the numbers based on just a few axioms, and we'll do that someday on stream. But yeah, this does not take very long to prove that 1 plus 1 is 2. But if you get even more rigorous, if you get even more formal, it takes hundreds of pages, and people are still arguing about whether or not 1 plus 1 equals 2, and it's a little silly. So, you know, be warned, if you start enjoying this kind of math, you might end up spending the rest of your life answering these kinds of questions, and that's, I don't know, that's a little too far for me. I love this kind of math. I love pure mathematics, but it's a little too far for me, even. Yes, that's it. I knew it was something like that. Yeah. Thanks, Lockheed. I appreciate that. All right, I'm done. Thank you for your attention today. We've already done 2.5 hours. So today was a working session. Tomorrow, I think I won't stream, and instead, I'm going to post a lecture. Tomorrow, Math as a Hobby, Lecture 1. I consider these streams, they're like co-working sessions. This is, I mean, it is kind of a lecture, but like I'm working problems with you all. I'm seeing them for the first time. we're working together in a discussion. But tomorrow is going to be a new video, and I'm going to film it privately on my own today. Please do keep an eye out for that and give it a watch. I hope that I hope it turns out well. I have something nice in mind, I think. So, math as a hobby. I don't know if I want to use that tagline or intro to pure math. Feedback is a gift, y'all. If you all want to let me know what type of title do you think is the most interesting and clickable if you didn't already know me. If you haven't already seen the streams, we've got Intro to Pure Math. We've got Math as a Hobby. Math for Adults. What do you think is most clickable? In any case, it's going to be Lecture 1. Intro to Pure Math may not get the intended target audience. See, I just don't even know. Yeah, I don't know. Because it is, in my opinion, an intro to pure math, and this, what we work today and what's in this book and how it emphasizes proofs is not that different from a discrete math course which introduces pure math and mathematical reasoning and proof writing. But somebody searching pure math is probably interested in new pure math concepts like discrete math or abstract algebra or real analysis. Whereas this is learning proof writing and an intro to the method of pure math in basic mathematics, in high school math. Yeah, you wouldn't associate pure math with middle school math based just on the title. Yes, it would be this title with this book let me see if I can get this thumbnail. I think the thumbnail looks nice. I've got a better way to do this. Give me 1 second. This is going to be, you have to imagine these titles next to this thumbnail. Hurry up, export. Why isn't it exporting? Okay. Dang, it's 10 megabytes. Okay, and of course, if I use Math for Adults in the title, I could change it in the thumbnail. But let's see, did that work? Yeah, all right, so here's the thumbnail. Integers and addition, basic mathematics, some kind of tagline in the bottom left. I think that this is a good book. This is the book that I recommend for you, Mohammed. This is the one. You're in it. This is it. These videos, I think, are like, if you want to get better at math, You see the vision now. Okay. So the title would be Lecture 1 dash Intro to Pure Math, Lecture 1 Math as a Hobby, Lecture 1 Math for Adults, or something. So you see it, you see the idea now. Opinions? Huh? I mean, it could be day 1 if I want to be social media-y, but I think Lecture 1 says something a little better. It's not an unstructured, just vibing practice stream. It's something that I filmed on my own before, that I pre-filmed. So let's remove this. My thought is Lecture 1, M dash. I'm using M dashes aggressively now as a minor protest to fucking AI. I don't like AI. I do not like AI. It's not going to take M dashes away from me. I like M dashes too much. What are your thoughts? Thomas Calculus is okay. Yeah, it's fine. I don't like it as much as the calc book that I'm using. This week is basic mathematics, and we're working through this book. Next week, we will be doing calculus. I like this book better than Thomas. Taalman and Kohn is more conceptual, and it's a really nice one. You'd expect Lecture 1 after the title. Yeah, it could be. Totally could be, yeah. I'm trying to think of some variations to Intro to Pure Math. I feel like it could be in the thumbnail, Intro to Pure Math. Author name Taalman for calculus. Okay, here we go. Thank you for asking. High school, middle school, pre-college, you know what I mean, like secondary school, high school. Let's just say high school. In the US, we call it high school, at least. High school, I'm working basic math by Serge Lang. College, I'm working calculus by Calculus by Taalman and Kohn. This is also in the video description, so you can find it there. And then for graduate level math, or research math, maybe you could call it, I'm working representation theory by Steinberg. We're now doing 1 week of high school math, 1 week of college math, 1 week of graduate level math, and then reset. So this is the structure that we're doing. Some of these questions are funny, man. Like, just, dude, like, if you want to learn how to get good at math, like, follow these streams. Like, I'm talking about that all the time here. That's what I'm doing all the time. Like, I'm just, I don't know, practice. Like, really just practice. If you want to get good at math, practice a lot. Work many exercises, even ones that were not assigned. And dude, also freaking make some friends. Dude, like, nobody told me to make friends in college, and I wish that somebody told me, to make friends. I think that one is missing. Make friends. Not just because we should all have a social life in school. Like, it's important to have a social life. It really is. I had a social life. But I did make friends with math people. Like, it's also very valuable to talk about math with other people. I think that those are my top 3 tips. Practice, work more exercises than you were assigned, and meet other math enthusiasts. Hang out in this stream. Like, in this chat, you're going to meet other people who like math and are hanging out and watching math for fun. So, yeah, never mind. Everything I think of sounds more like a book title than a lecture series title. Yeah, because, like, it's got to be YouTube-y enough, right? Like, I'm leaning toward... I'm leaning toward math as a hobby. Because I think that that's sort of like a unique idea that I emphasize more than I see any other YouTuber emphasizing. I feel like math as a hobby in the title and Intro to Pure Math in the bottom left. I think putting Pure Math in the bottom left, which has like a nice contrast of it is basic mathematics, it is high school math, but done in a pure math form. I guess that works. Yeah, my original thought was like I want to emphasize the idea that you can study math as an adult and that's okay, that's fun. But I think there's no reason to require saying adults. I think a hobby is inherently valuable to everybody. Like if you say that you do something as a hobby as a teenager, it's probably also a valuable hobby as an adult too. Like, hopefully you don't drop your hobbies just because you become an adult, right? Yeah. Does that make sense? I think I'm moving away from the idea of using the term for adults, and focusing on math as a hobby. Yeah, proving maths is maths. Yeah? Okay. Okay. Thanks for watching. I'm tired. Hope to see you all. Hope to see you all tomorrow in the, in the comment section of this new video. Would love to get your thoughts, and feedback is such a gift, y'all. We posted the first video, which we could call Lecture 0 or something, Intro to Pure Math video yesterday. So if you haven't watched it, this would be a great thing to watch next. Let me give the link, because I wish that I could raid my own video, but I can't. It looks like that's not an option for me. YouTube. So, if y'all want to help me grow as a YouTuber and, help us build a really cool, awesome community here, check out this video. Oh, it's already pinned, but yeah, I think that's a good video to watch next. Another good one, I keep doing this, and I hate doing that. Like when I'm video editing and I'm actually going back and watching myself and cutting out all the ums and dead space and dude, that's the worst. I'm trying to stop doing that and catch myself doing that. This would be a good video to watch next, or I like anything in my highlights playlist, honestly. Highlights. I think that my 2025 fact about the number 2025 is really good. I like that one. I think it's short and it does a really great job introducing proof by induction. So if you're curious, you could find that video about 2025 that I filmed last year when it had just turned 2025. I filmed it in January last year. Thanks for watching. Bye. I gotta go. Bye.